Alright, quick overview of the DJI Guidance and what we've implemented. So the Guidance provides ultrasonic sensor data, which it publishes as laser scans. And here we have them being displayed as these red dots. Unfortunately, the default laser scans provided by DJI doesn't have any angles. We had to specify angles in order for them to display up here. In addition to ultrasonic distances, it also published a more abstract obstacle distance, which is a mix of information from the stereo camera and the ultrasonic sensor. And we can see that in this giant white square, which is also a laser scan message. So in addition to the ultrasonic sensor for measuring distance, it does have two cameras for each sensor, which for stereo imagery. For two of the sets of cameras, the Guidance Core, the onboard computer for the Guidance system, can generate disparity maps, which is nice. It can also generate depth maps, but we didn't use the depth maps. We'll get to that later. So for the two remaining cameras, we had to generate disparity maps on the onboard computer using the left and right images. And after talking to a DJI engineer, we were able to match the parameters such that the disparity maps are the same across the board. So the default disparity maps don't have any filtering, so they're very noisy. So we opt for a speckle filter. Unfortunately, we couldn't do any pre-filtering because the disparity has been generated already on the Guidance Core, so we can only do post-filtering, such as speckle filtering. And the speckle filtering just gets rid of tiny little dots that normally appear everywhere. So this is fairly cleaned up image so far. And as I was saying, the reason we didn't use deformation directly is the deformation provided by the Guidance Core doesn't really match any standards that are typically used by ROS. ROS either uses straight up floating point RORs in meters, or it adopts the OpenKnee standard, which is a 16-bit unsigned integer in millimeters with no fractional bits. So and that's the standard we opt for, since OpenKnee is used mostly by various Kinect sensors. So from there we go, we generate depth images, and we do with those depth images, we generate point clouds. And here you can see a rough view of this living room. Unfortunately, there are 30-degree blind spots on these corners, so nothing you can see there. Alright, so let's take a look at the setup. So first, let's start with the Guidance setup. Here's the base link right here. That's the center gravity matrix that we specified. There's the Guidance Core. Then there's the various sensor. We had to mount the front sensor on top since the X3 camera was obstructing it. And just for extra accuracy, we actually map the left and right camera transformations, which, given the base link of 15 centimeters, results 7.5 centimeters more accuracy. All right, so let's take a look. So here we're looking at the front. Let me spin around. There we go, front. Sorry, my room's a mess. It's a house converted into a lab. Anyways, so as you can see, that was a very floral couch with a lot of patterns. As a result, the Guidance has the point cloud we generate has a lot of information. It's pretty much what we want, and you can clearly see it as an obstacle. Unfortunately, for the other areas of the room, especially this area under the desk, it's dark and not a lot of details. Here we have some details, specifically an April tag, and then my air filter, and then some various items on my table. But you can see giant white blank spots, and these are just plain white walls with no texture. And then finally, there's me. You can see my legs. The vertical FOV isn't very high, so you can only see up to my torso. Just to prove, let's take a look. And then there's the various camera views. And let's demonstrate the. So ultrasonic, unfortunately, has a very narrow view, so it's typically centered. So I have to get it right above it to affect it. I don't think I can. But the general obstacle distance takes into consideration the depth image. And here we can see when I kick my leg back, hopefully I don't kick the matrix, you'll see that it adjusts. Alright, so there's the depth image. So with the guidance, we also implement APRO-tag detection. This is mainly important for landing, since we will be using the downward facing camera for landing, but just as a quick demonstration, we have implemented for all 4 cameras. And we currently have an APRO-tag that runs multiple families at the same time, simultaneously. So here's a large 36H11, and in my hand I got the smaller 16H5. And you'll see this yellow line, that's just the TF link that matches to its coordinate. So there you see, it's currently on the right side camera, so the the transform link is to the right camera. And let me point this thing down, see if it appears behind me. There we go. Do you see the line? And let's see how far it goes. There, we lost track. So looks like it has a working distance of about 1 meter, a little over a meter. So this works on all four cameras. Not sure if I can demonstrate it without moving too far away. All right, but you get the point. See, you can see it popping up on the different cameras, and then finally the rear camera and the left camera. All right, hopefully I don't knock it over because it's barely standing up. So that's just a quick demonstration. These point clouds are used for obstacle avoidance and map generation. And we do use the guidance sensor to detect generalized quads as well. And those quads are useful for as highly potential APRO tags where we can point the X3 camera to verify. Because as I said, this is a 6 centimeter tag. That's only 16H5. The 25H9s are going to be a lot harder to detect. They probably have a detection distance of maybe half a meter, I'd say. And just to demonstrate that the depth image is highly dependent on textures, I got my blanket, which has a nice little pattern to it. Let's take a look. There we are, that's where my legs are. Flip it around. And we get a nice solid wall. Let me drape over here. And you can see the blanket right there. Same deal with the couch. So there you have it. This is what we've implemented so far. The different information is actually a lot better than I expected, especially with the point clouds it generates. The information is very useful for our obstacle avoidance and navigation. All right, that's all there is to it. I just demonstrated that it works with the various APRO tags. Again, let's flip it behind me. You can see it form the TF link right there. And then there's, of course, on the right side, the TF link to the much larger tag, which you can detect from quite a distance. Let me see if I can move it a little further. So let's take a look. All right, it's on the back of the couch. And yep, you can see the TF link all the way back there. So it looks like it has a working distance of about just a little over 3 meters. So that's actually very useful, especially for the final landing sequence. All right, and just a quick note, these cameras are running at 10 Hertz since I'm generating a lot of imagery information, specifically 4 sets of cameras and 2 sets of depth images. And that's unfortunately the bandwidth limitation on the guidance core via the USB 2.